Hello again, everyone. So we previously covered what is life in biology, and we then covered what is the nature of matter in chemistry. So for today, we're going to cover what is the nature of energy in physics. So life, matter, and energy, those are kind of like poetic in the sense of coming full circle. So again, before we just start on what itself is energy, we're going to look at just a recap of what physics is. Now remember, physics is the branch of science that deals with the study of the real world and its laws. Or you could think of laws as its rules, right? For example, how do different objects behave in different circumstances? So you could be talking about how an object might be falling towards the earth. Why does the object fall towards the earth? In what kind of manner does it fall towards the earth? As to the why, we don't have an actual explanation for. If you keep on asking why, and you keep on going deeper and deeper and deeper, we don't have an explanation for some of them. Some of the ideas, some of the concepts of the universe are just fundamental, and we can't go any deeper than that. Hopefully someone can go deeper than that someday. But as for the time being, a lot of the ideas that we have are based on some fundamental observations in the universe, right? Now, physics, again, is just to do with the study of real world interactions. And this is not necessarily to do with stuff like life. It's more so to do with stuff that is non-living, though it can also involve life, right? As long as, because you can incorporate these laws to anything that's alive as well as anything that's not alive. Now, anyways, energy is a good point to start off from as a topic because essentially everything in the world runs on energy, and you need to know what is the various forms of energy and why we even care about energy in the first place, right? Now, scientifically, energy is just the capacity to do work. Right, so I'm going to write that down. So that is the capacity to do work. So whenever we are doing any kind of work, we would call that some kind of energy that's involved in that process, right? So the more energy someone has, the more ability they would have to be able to get some work done. And that brings us to our second point, which is work done. Now, work done, scientifically, is defined as the transfer of energy or the energy transferred. Okay. Now, one thing that I hope you're noticing is that both of these definitions are kind of circular. Energy is the capacity to do work, and work done is the transfer of energy onto a system. So they are both kind of circular in that sense. And that's not without reason. It turns out that energy and work done are basically synonymous. They both mean the same thing. In some textbooks and in some lectures, you're going to hear people saying energy, you're going to hear some other people saying work done. But as I'm delivering this to you guys, I might be saying energy or I might be saying work done. And what I want you to remember is that energy and work done mean the exact same thing. There's no difference between them in a sense. The only minute difference is that work done involves a force that's acting on something, but that doesn't mean it's not a kind of energy transfer. It still is an energy transfer, but you can use it more in the context of it's the work done by a force. Or you can use energy more in the context of it's the energy generated by a force, for example. Okay? Now, there's a new term that's come up recently, which is to do with the concept of energy stores. Okay, I'm probably not going to be referring to this word as much, but I just want you to be aware of the fact that it exists. Now, an energy store is essentially something that can store energy, right? So, for example, a battery would have a certain store of energy in it. We ourselves have a certain store of energy right now. That's how I'm able to talk to you guys. If I didn't have an energy store in me, I wouldn't be able to talk to you guys, right? So everything out there has a kind of energy store, and things that have a store of energy, it's not necessarily that obvious that they have energy. Okay, so for example, with my arms moving around right now, my hands moving around, that is the kind of energy that you can see where my arms are actually moving around. But you can't actually see where that energy from my arms is coming from. It's actually coming from my internal store of energy, which is less obvious to see. So just keep in mind that when we're referring to something as an energy store, that usually means that it's a bit less obvious as to where that energy actually is visible. All right. So what we're going to do is we're just going to go through an entire list of every single energy that I can think of with regards to the universe. Okay. And we'll start off with the most obvious one, which is kinetic energy. Okay, kinetic is a term in English that just means to do with movement. Okay, so if anything is moving, we say that it is kinetic. So kinetic energy is the energy that's associated with movement. So associated with any kind of motion. Okay, and this has an equation behind it. The equation is written like this. I'm just going to use symbol Ke, but you can also use the symbol Ek, where you have E subscript K. The E will stand for energy, and the subscript K will stand for kinetic energy, or kinetic. But kinetic energy can be defined as half mv squared for situations where you have like low speeds. That's when you can define kinetic energy with this equation, where m is the mass of the object and v is the speed of the object. Okay, of which the speed is measured in meters per second and the mass is measured in kilograms. The energy as well is always in the standard units measured in joules, right? That doesn't mean that it needs to be in joules. It could also be in calories, but that's less conventional to be using unless you're a chef. If you're a chef, you'd be using calories as a unit of energy instead, because that's something that's more relatable to people. Okay, a joule is not as relatable. But this over here is what is the equation for kinetic energy. What this equation basically means is if you've got a truck that is double the mass of a car, if the truck moves at 10 meters per second, and the car also moves at 10 meters per second, based on this equation, the truck would be having double the energy as the car would have, because the truck has double the mass. In the same way, if you got a car and the car is moving at 5 meters per second, if you double the speed of that car, the kinetic energy of the car is not going to double, it's instead going to quadruple because of the square relationship in that equation over there. So something to just keep in mind that these are how quantities are affected in physics, right? And you're going to be seeing a lot of equations as we're going through physics, because math is, well, whether you like it or not, math is the language of how we can understand the universe better. So a lot of the laws here are underlined by equations and mathematical relationships. Either way, so that over there is just what kinetic energy is, and then we can move on to another kind of energy, sort of a very simple one, which is gravitational potential energy. The equation that I'm going to write down for you for gravitational potential energy also only works for distances that are very close to the Earth. If you go farther away from the Earth, it doesn't work anymore. But if you are staying near the Earth's surface, which we are, then it is essentially fine. So the gravitational potential energy is just defined as the energy stored by a mass within a gravitational field. So every mass out there expresses its own gravitational field. The gravitational field is just a field that reaches outwards from a center point of mass, which will pull other objects, other masses towards it. You can think of it as a net. So you have a mass in space, it's stretching out its net, and that net is catching other masses to pull towards it. So right now, for example, our Earth is constantly in a pull towards the sun. We are caught in the sun's net of gravity, if you will, right? So the Earth has a gravitational potential energy that it gets from the sun. And in the same way, we are caught in the Earth's net. So we have a gravitational potential energy that is caught in the Earth, right? So again, like I was saying earlier, this equation here only applies if you are close to the planet's surface. And the equation in this case is that dPe, right? The gravitational potential energy, which you can also write as Eg if you wanted to, but I'm just going to say that gravitational potential energy is defined as mdh, where m is the mass, d is the acceleration due to gravity. So it's inaccurate to say that g is just gravity. It is the acceleration due to gravity, or you can call it the gravitational field strength. They're both equivalent. See, and this over here is measured in meters per second squared, whereas the gravitational field strength is measured in newtons per kilogram. Okay, so Newton is just a unit of force. And again, both of these terms here are different to gravity, because remember, in gravity itself is just a concept, right? Gravity is the concept that causes that force to actually work, or it's the name that we give to gravitational force. It's the concept of gravity. It's the fact that masses pull on each other, right? But the acceleration due to gravity is the acceleration that a gravitational force causes. And the gravitational field strength is the force of gravity per unit mass that's acting on some kind of mass in that gravitational field. And then finally, that GPE is just the gravitational potential energy, which again is still measured in joules, right? So this over here are the is kinetic energy and gravitational potential energy, and these are the equations for them, right? The other point as well that I just want to mention is that if you look over here and we look at the unit for energy, which can be like J or joules for long form and then J for short, you will sometimes hear about something like kilojoules and megajoules being mentioned, right? These are scaled units. So the base unit, let me just go on a bit of a tangent here, just so you're aware of this. The base units would just be joules, for example. One step above joules, which is 10,000, that would be kilo, which is 10 to the power of 3. Right? So meaning that 1 kJ, 1 kilojoules, is 1,000 of the base units. So that's 10 to the power of 3. 10 to the power of 6 would then bring us to mega. 10 to the power of 9 brings us to giga. 10 to the power of 12 brings us to tera. And 10 to the power of 15, I believe, brings us to exa. And below this, we have some units as well. 10 to the power of minus 1, that is deca, or deci. 10 to the power of minus 2 is centi. Deca is actually up here, by the way, but we don't use that as much, so I'm not going to mention it. 10 to the power of minus 3 is milli. 10 to the power of minus 6 is micro. 10 to the power of minus 9 is nano. And we've also got 10 to the power of minus 10, which is Armstrongs. And finally, we have 10 to the power of minus 12, which I believe is going to be either pico or femto. I do believe it's pico. And then after that, you got 10 to the power of minus 15 as well, which is femto. But the base units are just the base units. The symbol for deci is D. The symbol for C is C, or centimeters is C. For milli, it's M. For micro, it is this Greek letter here, which is called mu. For nano, it's N. For Armstrong, it's A with a funny letter of O above it. And then for pico, it's a small p. And above base, we've got K for kilo, capital M for mega, capital G for giga, capital T for tera, and capital E for exa. So usually if something has a bigger scale, we use capital letters for it. The only exception is kilo. Okay, so for example, you could say that 1 megajoule is the same as 1,000 kilojoules, right? Or you could say that 1 millijoule is the same as 1,000th of the base unit of joules. So that's how the scale over here actually works. And the reason why we have the scale is because sometimes you might be dealing with objects that are very huge, which is the case of planets, or sometimes you might be dealing with objects that are very tiny, which is the case for atoms, right? So what scale you're using depends on what you're actually investigating. So in the case of us, using joules is usually just fine. But if you're talking about stuff like cars, you might want to use kilo. If you're talking about stuff like the energy consumption of an entire country, then you might want to be using giga or mega instead. So that is the kind of scale difference. And we use these scales because we don't write so many zeros in our numbers all the time. But anyways, going back to this then. Okay, so we have kinetic energy and gravitational potential energy. So again, just to give you an example, kinetic energy is associated when something is moving really quickly. Gravitational potential energy is to do with the stored energy in a gravitational field. So if I've got this pen over here, which you can see, if I raise this pen up a little bit, then it's going to have a higher store of gravitational potential energy. That's basically what's happening. And the reason why that's the case is because the height of the pen from the ground is increasing. So it's got a higher store of gravitational potential energy. And if I bring it lower down, then it's got a lower store of gravitational potential energy, right? Notice as well how the pen is always more stable when its height towards the ground is 0, meaning that if the pen was kept on the surface ground, then it would be fully stable. But if the pen is kept really high up, then it's actually more precarious, it's more unstable, because you can suspect that the pen might be falling at some point, right? So there is a bit of a relationship between energy that something has and the stability of something. So just keep that in mind as we go along here, right? And that's also another reason why teaching about energy is really important. But anyways, apart from gravitational potential energy, we then also have chemical energy. Okay, now chemical energy is the energy that's stored in chemical bonds. In chemical bonds. which, if you think about it related to chemistry, chemical bonds are caused by electrostatic attractions between two substances. So chemical energy really is just a type of electrical energy. We'll move more purely into that after. But again, chemical energy is the energy stored in a chemical bond, and that in fact is how I'm able to talk to you right now. The kind of store of energy that I have in me right now is the chemical energy from the food that I've eaten this morning, right? So the reason why we even eat food itself in biology is because we need energy from somewhere. So every time we are eating food, what we're really doing is we are replenishing our chemical energy reserves, and those chemical energy reserves are used for other things, like the energy that I'm using to talk to you right now. Okay. Now, the form of chemical energy is a bit complicated. You will learn more about the form of chemical energy from experimental formulas once we do higher level chemistry. And if you're curious about this, you might want to read up on enthalpy. This again also links towards electrostatic potential energy. Okay. In case you're just curious, enthalpy is basically the store of, well, it's the energy that's released to an environment based on how much energy the molecule has had. So, for example, if you've got a reaction where maybe hydrogen is reacting with oxygen to make water, if the molecules as a whole have lost 10 joules of energy, then it means that the thermometer reading on the outside would have measured that increase in energy to the environment, because that energy from the molecules is being lost towards the environment instead. We refer to this concept as enthalpy as it helps us measure how much energy was actually originally stored in the molecules, right? But that's just an example. And again, enthalpy really is derived from the electrostatic potential energy between the atoms. So that's to do with the electrostatic attraction between them. So I'm not going to go through the equation for it just yet because it's a bit complicated, and we'll revisit that some other time in the future. But electrostatic potential energy is basically the same as gravitational potential energy, but instead of the energy being stored in a gravitational field, electrostatic potential energy is the energy stored by a charge in an electric field, right? So every kind of force out there exhibits itself as a field, or we can better understand them in terms of fields. Like we've got the gravitational field for gravitational forces, and we've got the electric field for electrostatic forces. But okay, then just moving on. Apart from that, we also have electrical energy. This is different to electrostatic potential energy because electrical energy is associated with the energy that's transferred by a circuit. And this will make more sense once we go more into detail on this. But again, electrical energy is the energy transferred within a circuit, like the circuits that are running the lights of my room right now. And for electrical energy, we define it with the equation E equals VIT. And you could put a small e there for electrical energy if you wanted to, or just use double E for electrical energy. Now, electrical energy, again, is still defined to be in units of joules. V over here is the voltage, which will make more sense once we come across it again. I is the current, which is measured in these units of amperes, and time, and T over here is the time. So again, I will revisit electrical energy in the future, but just so you have a brief understanding of it, the voltage is a number on the battery which tells you how much energy that battery is transferring for some amount of charge. The current tells you how much charge that battery is outputting for some amount of time. And time over here says how long you've been running that battery for. So if you know what's the voltage of a battery, and you know what's the current, and you also know how long you've switched that appliance on for, you can measure the electrical energy by just multiplying those three numbers together. Okay, that's the point of the electrical energy equation. And then we have another energy that I think is very important. This over here is heat energy. And if you study thermodynamics, which is the branch of physics that's literally to do with the study of how heat evolves in systems and how heat interacts with systems, you will have a love-hate relationship with heat energy. Heat energy is one of those concepts that drives the universe, but it is also a consequence of everything, in the sense that any process that we ever have, where we're converting energy from one form to another, you can be certainly guaranteed that there will always be some amount of heat energy that's generated from that process. Even right now, as I'm talking to you, some of the energy that I'm using for my chemical energy, some of the energy is not fully transferred towards you. Some of it is just transferred as heat energy, which is escaping to the environment. So this concept of heat energy is actually quite important. Now, again, heat energy, you can just define this as the energy due to the individual So again, this is the very scientific definition of heat energy, right? Because if you think about what heat energy actually is, it's kind of hard to define. If you touch the surface and you say that it's hot, like, can you define it by saying that heat energy is to do with hot surfaces? But like, then what does it mean to be hot in that case, right? So here's the definition again of heat energy. So it's the energy due to individual motions or random motions of particles within the substance. So this is not to be confused with kinetic energy, okay? When we're talking about kinetic energy up there, we're usually referring to the kinetic energy of the system as a whole. So you can imagine we have a box of water, and on that box of water, we are moving that box of water around. The whole system is moving with that amount of kinetic energy. But with heat energy, it's a bit different. Heat energy is a microscopic quantity, meaning that it comes from the system on a microscopic scale, right? So if I've got that box of water and I don't move it, all the particles inside the water will still be slightly shifting and moving around, right? So if the temperature of that solution was really high, then the particles would be moving really quickly. And if the temperature was very low, then the particles would not be moving very quickly. And that characterizes how much heat energy something has. Okay, so if you touch a metal pan, for example, the reason why you would feel a burn is because the particles in that metal pan are vibrating very quickly, and that causes friction, which will heat you up, right? But that's to do with heat energy. So again, it's the sum of the kinetic energy of all the particles in the substance. That's what heat energy actually is. And you will see us mentioning heat energy twice in two other equations, one of which is called specific heat capacity, and the other is called specific latent heat. I'm just going to write down the equations for them first. Specific heat capacity is characterized by this equation, where you have the heat energy being equal to the mass times the change in the temperature, which is over here. That triangle means change. This C over here is actually the specific heat capacity, which has these very confusing units over here. And T over here says the temperature, which is measured in degrees Celsius. M is, again, the mass. E is the heat energy associated, right? And if you're wondering what specific heat capacity is, specific heat capacity in a nutshell, again, we will come to this point a bit more in depth later on in the future, but that's in a nutshell. Specific heat capacity tells you how easy it is to change the temperature of something, right? So for example, if you've got a substance where you give it a bit of heat and then you put a thermometer next to it, and you see the thermometer jumps sky high really quickly, then it means that the substance has a low specific heat capacity, meaning that you can provide it with a lot of energy and its temperature raises up really quickly. But if you have a substance where you're giving it a lot of heat energy, and despite giving it a lot of heat energy, it just takes ages for the temperature to change, then that substance has a high specific heat capacity, right? So you can think of specific heat capacity as a quantity that characterizes how much heat energy something can store per unit of temperature. So water, for example, has a very high specific heat capacity, which is one of the reasons why water becomes so important in biology, because water can be used as a mediator, as a coolant, to help cool body systems, for example. That's the reason why we need a lot of water. That's the reason why we sweat if we are feeling overheated, and so on, right? But that is the advantage of using water. It has a uncharacteristically very high specific heat capacity for a fluid compared to, I think, just about any other fluid that we know in the universe. Now, apart from specific heat capacity, the other energy associated with heat energy is specific latent heat, which has this equation here. Okay, so the amount of heat energy given to a substance is equal to the mass change. This triangle again means mass. Oh, sorry, it means change. And this is the Greek letter capital delta. So delta M means change in mass, and L over here is the specific latent heat, which is measured in these units of joules per kilogram. Now, specific latent heat characterizes how easy it is to cause something to evaporate, or to condense, or to freeze, or to melt, or to sublime, and so on, right? Or to solidify. So basically, it's the energy associated with the change of state of matter, right? So if something takes a very long time to turn from a liquid to a gas, then it means that it has a high specific latent heat, right? So if you look at water, for example, water would have a very high specific latent heat for turning from a liquid to a gas, but it would have a low specific latent heat if you're trying to turn from solid to liquid, because it's easier to melt things as compared to trying to evaporate them completely, or not evaporate, but boil them completely. Okay, now these are the energies that we covered so far. And there's one more energy as well, which I'll just mention really briefly. One of which is magnetic energy or magnetic potential energy. This again is just the energy stored in a magnetic field. I'm going to use the word B field for it because in physics, B usually refers to magnetism. So I'm going to just use B field rather than magnetic field. And then apart from magnetic potential energy, we also then have nuclear energy. Now, you really will only learn more about nuclear energy if we go into this in more in depth. But just to give you a bit of an example of what nuclear energy actually is. Nuclear energy is the energy that's stored in the nucleus of the atom. So it's the energy stored in the nucleus of the atom. Okay, so remember, usually if there's a force involved, there's always a corresponding energy associated to it. Okay, either a force or a momentum. So, for example, with chemical potential energy or chemical energy, which is the consequence of electrostatic potential energy, that is the energy that's derived from a consequence of electric forces that are pulling onto objects, right? So nuclear energy as well is the result of a force that is within the nucleus of the atom. And we will learn more about this force. It's called the strong nuclear force. We will learn more about this force as we go into it. But that is what the nuclear energy is derived from, right? And this is the very same kind of energy that's responsible for things like nuclear power plants, atomic weapons, and so on, right? That's what this energy is associated with. It's also associated with things like radioactive decay, which is when you have an unstable nucleus and it starts to decay into something else, right? So all of that is to do with nuclear energy. And the equations for nuclear energy are too complicated. We have some approximations for modeling it, but right now it's still an area where we don't really have a one-all equation for every single nucleus out there. It's pretty complicated to model because we're dealing with scales that are very tiny, and we're also dealing with nuclei where the particles are arranged in a very messy kind of situation. So it's very complicated to model. But anyways, just moving on to the next one, we then have elastic potential energy. Now, elastic potential energy is simple enough that I can actually tell you what the equation is. And firstly, this is the energy stored in elastic materials. But really, it's derived from electrostatic potential energy because that is where that energy is coming from. When you have an elastic material, so stored in elastic materials, if you have an elastic material and you pull on that elastic material, right, what will happen is you're stretching the chemical bonds of the material, which means that you are increasing the electrostatic potential energy. So again, elastic potential energy is just another kind of electrostatic potential energy, but we refer to it by its more common name, elastic potential energy instead. So if you think about an object like a slingshot, for example, where you have this rubber band and you're pulling the rubber band backwards, you let go of it and then an object goes flying ahead, that is elastic potential energy that you have transferred to that substance when you're pulling on it, and then when you let go of it, the elastic potential energy is redeemed into something else instead. Okay, so again, that is elastic potential energy in a nutshell for you. And then after elastic potential energy, the equation for it you should know is given by EPE equals half Fx. So EPE is the elastic potential energy, which is still in joules. F over here is the force applied on the elastic material. And X over here is the extension, which would still need to be in meters. Okay, so all of these quantities in these equations, they need to be consistent, or you can always just convert them to their base units. You can also rewrite this equation as half kx squared. Okay, k is a quantity that you will learn more about later on, but k essentially stands for the stiffness of the material, which is measured in newtons per meter. It basically quantizes how easy it is to stretch a material. So the value of k for an easily stretched spring would be very low, and the value of k for a very thick and heavy spring would be very high. As in, you'd need more force per unit mass, or per unit. You need more force to extend it for some amount of meters, basically. Okay. Now this over here is the equations for elastic potential energy. There is one last energy that I'll just mention, which is light energy. Oh, actually, it's two more now that I think about it. But one of the energies is light energy, and light energy is the energy transferred by light. Transferred by electromagnetic fields, which is this light. Okay. Now this has an equation which is called E equals hf. You don't exactly need to use or worry about this equation just yet. We'll go more in depth into it later on. But just if you're wondering what this is, E is the energy of light and F is the frequency of that light. So just be mindful that the energy of light depends on the frequency of it. So if you have high frequency light, which would be something like blue light, that has a high amount of energy. But if you have low frequency light, which is something like red light, that would have lower amount of energy, which by the way is the reason why blue light, for example, activates the eyes. It makes it harder for you to sleep. It's because blue light has a higher energy associated with it, whereas red light is not as activating because red light has a lower amount of energy. There's a bit of a caveat to this, I suppose, which is the fact that when I'm talking about energy here, I'm really talking about the energy of a single light particle, which we call a photon. This is a bit different to intensity, which is how bright a light source is, but these facts, I suppose, will make more sense once we go into this in a deeper level. Okay, but for the time being, you can just be aware that this is an equation that exists. If you're wondering what H is over there, H is one of the most important constants in quantum mechanics. We call H the Planck's constant. And again, where this constant comes from will make more sense later on. Okay, but anyways, the last energy that I will mention, and this definitely is the last now, is sound energy. And this again is the energy stored by a sound wave, or the energy transferred by a sound wave. Okay, now you might be wondering from all of this, why have I gone through this exhaustive list of energy? Like, what was the point of all this? The reason why is because with every single kind of energy out there, you can characterize energy transfers and energy flows in any system in the entire universe if you knew about what energies make up the universe in the first place. Okay, and the reason why all these are really important is because of something that's called the law of conservation of energy. Okay, the law of conservation of energy isn't exactly a law, as in more it's an observation of what we've seen so far. There are some kind of exceptions as to where it doesn't apply, I suppose, but for 99.9% of cases, it will always apply. Now, the law of conservation of energy states that in any closed system, the any form of energy can only be converted from one form to another, but never on its own be created nor destroyed. Okay, so this over here is the law of conservation of energy. All right, so just back to what I was saying. With the law of conservation of energy over here, the reason why this is a very powerful statement is because it tells you that if you've got 10 joules of any kind of energy, say chemical energy, that 10 joules of chemical energy can be converted into another kind of energy, like heat energy or sound energy or whatsoever. But the energy needs to be conserved, meaning if I had 10 joules of chemical energy that was converted into, let's say, 3 joules of sound energy, then the remaining 7 joules of energy needs to express itself as another form of energy. Well, or all of it's converted to sound, which is usually impossible because there'll be some waste energy that's produced, which would probably be heat energy. Okay, and again, the reason why all this is really important is because if you can understand, if you can memorize what the different kinds of energies are in the universe, you can look at the universe in a completely different way. You can look at the universe as a system of energy transfers, and that explains how the world itself works. Right? This is very integral to biology, for example, because biology is all about energy transfers. Biology is all about trying to keep energy in place and trying to maintain that energy store for as long as possible until we inevitably perish from aging and entropy, right? But either way, just to give you an example, what I'm doing right now to you guys, what I'm doing is I'm using my chemical energy store and I'm burning up those calories in me. That is a unit of energy, by the way. With calories and joules, they're both the same thing. But I am burning up those the chemical energy in me through the process of respiration, and that is producing the kinetic energy in my vocal cords here. That kinetic energy in my vocal cords, which causes the vibration of the vocal cords, that is vibrating against the air, and that transfers the kinetic energy into sound energy in the air. The sound energy in the air is then transferred to my microphone, and even before the sound energy is made, as well as the sound energy being made by my vocal cords, it's also heat energy that's being made as a waste energy. So that heat energy is actually warming me up. So what biology tries to do is biology tries to maximize the most of its wasted energies, because that's the most efficient way to work things, right? So you can see that in the case of biology, heat energy isn't exactly a waste per se. It's more so that it's welcome because we need that optimum temperature to keep our engines running, essentially, right? So you can see that in the case of biology, it's a big adaptation of systems that is trying to maximize the efficiency of every single process, right? Anyways, now with the vocal cord having produced kinetic energy and sound energy, that sound energy is going into the microphone. The microphone converts the sound energy into electrical energy, into electrical signals. That electrical energy goes into my antenna. The antenna will then transmit those electrical pulses into electromagnetic pulses, which are light waves. Those light waves, which are radio waves, will then transfer all the way up into the atmosphere, into a satellite. And then that electromagnetic energy from that satellite will be reflected downwards to your location, right? And then your antenna at your location or your device will pick up on that electromagnetic energy, and that electromagnetic energy on your device is converted into light energy, which you are seeing, as well as, first it's converted to electrical energy in your circuits, and then it's converted to light energy, which you're seeing, or it's also converted into sound energy, which you're hearing, either or both. And some of it is also dissipated as heat energy, which is wasted to the surroundings. And then when your eyes will pick up that light energy, what's actually happening is the light energy from the device is entering your eyes. The retinal layer of your eyes will pick up that light energy and convert it into electrical energy, and then that electrical energy will be used by your brain to process the information. So it comes full circle, right? So you can literally explain any process in the universe using energy transfers. So it's a very powerful tool because not only can we use it to solve problems, but because it should change your mindset of how the universe works, right? Everywhere you look, it's impossible to find a situation where there is not an energy transfer involved. There's always an energy transfer involved in any kind of situation. So you can model situations using energy. The only downside of energy is that when we're talking about energy, usually the source of direction is lost, right? For example, energy doesn't have a direction associated with it because energy is a scalar quantity, right? When I tell you that I have chemical energy in me, where is that? Like, does it have a direction? Is it chemical energy up, down? Like, what is the direction? So chemical, like, energy doesn't really have a direction to it. And this is especially the case for heat energy, for example, because heat energy is literally random motion. So how can you measure that? How can you measure that for every single particle? It's basically impossible because we don't have technology that's that high, right? But that's just one thing to keep in mind. But either way, it's really important that you keep this lens of thinking with you. When we're talking about topics in chemistry or in biology or even in physics, always think about the corresponding energy transfers, and that will help you make more sense of the situation that's going on, right? At least in the concrete kind of level. Now, in that little speech that I was giving earlier, there was another quantity that I mentioned really quickly, and that was actually efficiency. Now, efficiency is another quantity that is important in terms of energy, because it's mostly useful for engineers. It's also useful for biologists in the sense of it tells you how efficient a reaction is, and therefore it's also useful in chemistry to some regard as well. But efficiency is just a metric that we use to determine how efficient some kind of system is, right? And it's defined as the total energy input at the bottom, and then the useful energy output at the top, and you multiply that with 100. Now I prefer writing it in the shorthand, which is small e equals EI by EO times 100. And the 100 there is just if you want to convert it into a percentage. It's not like you need to convert it to a percentage, okay? But just to give you like a bit of an example, if you have a kettle, so this is my weird kind of kettle that is plugged into the socket, right? So if I have a kettle that's receiving electrical energy, that kettle is going to be receiving all that electrical energy, and it's going to be dissipating that electrical energy into heat energy, as well as some sound energy that will dissipate into the environment, right? That's what we hear from the steam of the kettle. Okay, so we've got heat energy and sound energy that's produced from the electrical energy. If we suppose that we have 100 joules of electrical energy and that we've given the kettle, ignoring the heat that's transferred to the surroundings, okay, if we give the kettle, let's say 90 joules of the heat energy and 10 joules of the sound energy, then the efficiency of this kettle would be 90%. Okay, one thing that's very important for you to just notice is that if you look at any system, there is always going to be some amount of wasted energy produced. I mean, of course, there are ways for the system to get around that. For example, the system could try to use that heat energy to its benefit, which is the case for biology, for example, right? But even then, with the heat energy, it's not easy to store all the heat into a specific box. There is going to be a slight radiation of the heat that's lost to the surroundings over time. So in any system, the efficiency can never be 100%. It's always going to be lower than that 100%, meaning that if you ever have someone that's selling you a device, and if you want to know whether they're calling you or not, you can check what are the power ratings of the device, and you can do the math yourself to calculate what the efficiency is of the device by using the equations that we wrote about up there. And if you see that the efficiency of the device is above 100%, then it means that the person is lying. Because if the efficiency is more than 100%, then it means that the person has violated the law of conservation of energy. And if the person has done that, then they really should be trying to get their Nobel Prize, and they should be proving it in science. But it's likelier instead that they're just trying to con you, right? So again, that's something to think about. That efficiency cannot be above 100% because we can't violate the law of conservation of energy, and it can never be 100% because there's always going to be some amount of waste energy that's dissipated to surroundings. If you're going to ask me why that's the case, all I can tell you is that that's just an observation that we've made. In every system that you look at so far, basically seems that even if it's heat energy that's a useful product of it, some of that heat energy will be dissipated to surroundings, which, makes it wasted energy in some proportion. Okay, but that is the formula for efficiency. Now, apart from efficiency, there's another useful metric that engineers use, which is power. Right? Now, power is defined as the rate of energy transfer. Okay, the reason why power is important as a concept is because if you are trying to buy a device, knowing how much energy that device produces is not really that helpful. For example, I could tell you right now that I generate 1000 million joules of energy, and I wouldn't be lying to you. I definitely do generate 1000 million joules of energy, but it's across my entire lifespan, right? So what really matters more to engineers is the amount of energy generated in a particular amount of time, because that quantifies whether something is more useful or not, right? So here's the equation based on the definition of power. Firstly, power is measured in watts, and it has this equation here, that power is equal to E over T. So it's the energy transferred per unit time. And that there is just the power, which again is measured in watts. Okay, so if you've ever seen the word W or the letter W before on a kettle, like kW, which is kilowatts, then that just means that that kettle is producing 1000 joules of energy in one amount of second, which also tells you how much energy that is draining out of your electricity bills, right? Because if you know that something is generating 1 kW of energy, then you know that it's using up 1 kW of your electrical energy or per second, right? That's what's actually happening there. Now, apart from that, you should also know about the typical formula for work done. If I just go back up here. Okay, remember that work done, when I was talking about it earlier, work done is usually associated with forces. Okay, so when a force does something to an object, like it pushes the object and so on, then we can say that the force has done some work on the object. But in science, we define the work done to be only occurring if the object has moved in the same direction of the force. Right? So here's a more technical definition of the work done. We say that it is the product of the force applied on an object and the distance moved in the same direction of the force. So here is the equation for it, that very classic W equals FD. And you would be seeing this equation even at university if you were doing physics, just in a more complicated form. But anyways, this is the equation for the work done onto some kind of object, which is dependent on its force. Many of the equations that I've written down here can actually be derived from this definition over here. So just to give you an example, if we look at GPE, GPE is the energy derived from the gravitational force times the distance. The gravitational force is dependent on the mass of the object and the gravitational acceleration. So that's mass times acceleration. And that is then multiplied with the distance, which is actually just the height. So you can see that every single force that we've actually, or every single energy that we've actually written off, or written about, actually comes from this equation here. That work done is equal to force times distance. Now, it's not necessarily just the number of force times the number of distance. It can also be expressed as the area of some kind of graph. For example, if you have a graph where you have force and distance, oops, sorry about that. Right. So if you have a graph where you have a force and distance, then this line over here, if I draw a line and I wanted to find what was the area underneath this graph, okay, that would actually give us the work done on whatever system this is, right? Because it's multiplying the force and distance together. So the area of a force and distance graph actually gives you what is the work done on an object. And this is more helpful if you can't just use the equation W equals Ft. W equals Ft is a bit of an assumption, I suppose, that the force is always constant and the distance is just some fixed value. But if the force isn't constant, as you can see in this case, the force is actually not constant, it's not a straight line, it's going upwards like this, right? Then you'd have to just plot the graph and find the area of the graph to get what's the work done. And that actually is how we figured out what is the work done for, where is it? The elastic potential energy, if I can find it. Yeah, right here. Okay, so if you have a spring, if you do an experiment to plot what is the force on the spring against the extension of the spring, that will end up giving you a straight line. And the area underneath that line is actually going to give us an area of a triangle. The area of a triangle is half times its base times the height. So half times its base is the extension and half times the height is the force. And that's what gives us that equation over there. So again, all of these equations over here have been either experimentally derived or they have been derived from the definition that we have set out for what is work done and force and distance. Okay. Okay, the last thing that I just want to mention is in terms of what I've said earlier with wasted energy, right? Be mindful that when someone says that energy is wasted, that doesn't mean that the energy is magically gone from existence, right? It also means that the energy is now no longer useful to us. It's been dissipated. Dissipated just means spread it out to the environment, right? So right now I've got some heat energy in me, which is slowly wasting away because that heat energy is spreading out to the environment around me. It's heating up the room that I'm in. Right? So just be mindful when someone says that energy is wasted, that doesn't mean the energy is disappearing magically. It more so means that the energy is just fading into the environment and it's no longer easily accessible or useful to us anymore. Okay? The other point as well is just in terms of the world that we live in, you should be aware that we derive the energy that we use from renewable and non-renewable sources. Renewable sources are energies that can be replenished very easily, and non-renewable sources are sources of energy which can't be replenished that easily. So in the case of a non-renewable source, that would be something like coal and oil and so on. That's all chemical energy in the world that we live in, right? But if we look at, let's say, light energy, which is solar energy, right? Or wind energy, which is the kinetic energy of the wind, or tidal energy, which is due to gravitational potential energy of water, that's all renewable energy because it lasts for a very long time and it's guaranteed to come up the next day. Okay, nuclear energy as well, which we use, that's non-renewable because at some point we're going to run out of nuclear reserves. Not for a long while now. But that again comes from nuclear energy, which is the energy stored in the nucleus of the atom. So you can appreciate a lot more how the world works, where we get our energy from by understanding energy. Another point as well is just that you should be mindful about the efficiency of a substance. Okay, so for example, if you're ever buying an appliance for your home, if you're contemplating how useful an appliance is, you shouldn't just be looking at its power output, you should also be looking at its efficiency, right? So for example, you might see a bulb that has a low price and a bulb that has a high price, and you might be tempted to buy the bulb that has a low price, but you really should be asking yourself, why does the bulb have a high price? And one thing to consider is what is the efficiency rating of that higher priced bulb. If the higher priced bulb has a higher efficiency rating, then it just means that in the long term or in the long run, you will end up saving more energy and more money from electricity bills on that initially more expensive bulb. than buying the bulb that has, a cheaper rate, I suppose, right? So that's something to also just consider in terms of the usefulness of a substance. So based on this, there's a lot of different environmental issues that can arise if you think about energy transfers in the world that we live in, right? The main issue right now is the world's usage on coal and fossil fuels as an energy source. Not that I'm trying to say that it's a bad thing, but what I am trying to say is a bad thing is the fact that it generates carbon dioxide emissions into the atmosphere. But the even bigger problem, in my opinion, is the fact that it's not going to last forever. So we really need a way to shift from sources of energy which don't last forever towards more sustainable sources of energy which will last forever. Or at least for longer durations of time, like nuclear energy and nuclear fusion instead, which is something that we're experimenting more on. We're making some amount of progress, but that is something to just keep in mind, right? So the reason why, for every country in the world, majority of the energy right now is derived from fossil fuel, which is going to put many countries in a pretty bad situation if we ever run out of fossil fuels. So as long as we don't run out of fossil fuels, then it's fine. But there is going to be a point where we've exhausted our fossil fuel reserves, and unless we've come up with a way to make up that missing energy that we are using in all of our houses, people are going to be in a lot of trouble otherwise, right? So again, the most promising thing right now seems to be nuclear fusion or nuclear energy, because if you compare nuclear energy for its energy per unit mass, which basically means its efficiency, compared to fossil fuel energy, remember, that is derived from chemical energy, okay? And nuclear energy, that is derived from the energy in the nucleus. The energy of the nucleus is way more energy efficient than the energy from chemical bonds. It produces way more energy if you have the nuclear energy being used up in the nucleus rather than the energy from a chemical bond being used up. Okay, so that's just something to keep in mind. And again, right now, the biggest kind of the most promising energy source that we are working towards right now is nuclear fusion. So right now we're using a source of energy that's called nuclear fission, which runs it's the second most used source in every country, basically, right? The first most used source is fossil fuels, but the second most used is nuclear energy, right? So that's quite good, but we can produce exponentially more energy with nuclear fusion instead. And the nice thing about nuclear fusion is, as opposed to nuclear fission, with nuclear fission you're going to produce some waste which is radioactive and harmful for the environment, but with nuclear fusion you actually produce no waste for the environment. Literally the only waste is water that's made from the fusion reaction. Well, or water being used up, I suppose, and then you're producing helium essentially, and some maybe iron at the end if you manage to get to that point. But that's also, again, there's something to consider about. Apart from that, be mindful about the fact that although this is to do with physics, energy transfers are everywhere in every science around us, right? Whether it is chemistry, or whether it is biology, or whether it's not even the sciences but your everyday life, there are always energy transfers involved. And again, you would do yourself a favor to think about what are the energy transfers involved, what is the efficiency of a process, and what is the power output of a process. And remember, power output is not how much energy is produced, it's how much energy is produced in a particular amount of time. Okay, and if you have these quantities in mind, a lot of the things in the world will make a lot more sense in a different light. For example, the reason why bats can even hibernate during the winter is because during the winter their power output is really low, but in the summer their power output is higher. So, for example, in biology, metabolism is just a fancy word for power output. That's really what it is. The sum of chemical reactions in the body, that is power output, right? If someone has more chemical reactions, that means they're extinguishing or replenishing or getting rid of more chemical energy in their body, right? So metabolism is just a kind of power output. So again, something to just think about, that life is really a race for seeking the most efficient ways to harvest energy and to use the energy and to store the energy efficiently. That is what life is about. And chemical energy, or rather chemistry, that really is all to do with energy and stability, more importantly, right? So I mentioned this at the beginning, and that's the last thing that I will mention before I end this, which is just the relationship between energy and stability. What you need to understand is that when a substance has a lot of energy stored in it, it becomes more unstable, because it needs to relinquish that energy to its surroundings. If a substance has very less energy stored in it, it becomes more stable. If a substance has less energy or more energy stored in it, then it becomes more unstable. Okay, so again, more energy means more unstable, less energy means less stable. I mean, more stable. So I'm mixing it up. So just to give you an example, if you got TNT, TNT has a lot of chemical energy stored in it. So it is highly unstable before it's detonated. Once the TNT is detonated, it is going to convert its chemical energy into heat energy. So once all the molecules have lost the chemical energy into heat energy in the environment instead, the molecules now have lower amount of chemical energy. So the molecules are now having lower energy, so the molecules are now more stable, right? So that, again, you can link that to biology. Biology is all about maintaining that stability level that the organisms have, right? Because every organism on the planet is always on a constant fight of maintaining that stability. We're always losing energy to the environment, right? So what every organism is trying to do is every organism is always trying to maintain its stability levels, maintain its energy levels so that it can survive. As long as we can do that, we're alive. So that's another way of thinking about what life is. Life could just be defined as the perpetual fight for maintaining a constant energy reserve within designated levels. So that's something to think about. Yeah, so for next time, what we will go through is we will go through a bit on electricity in physics, and then in the next lesson, we will be continuing on biology again. So we left off on organelles last time for biology, so we'll be continuing from that point onwards. Right? So again, please support me on Patreon if you've enjoyed this lecture. And if you have any questions or any suggestions for topics you'd want me to cover in the future, just let me know in my comments. If there was something that you didn't like as well, do let me know because I'm always eager to improve. All right. Thanks for listening and see you next time.